Okay, so this is a review of chapters 2.1 through 2.3, which is the first part of the polynomial unit. So the unit starts off with simplifying exponents and using our exponent properties. So whenever I look at something like this and it wants us to simplify, the first thing that I'm going to look at is anywhere I have parentheses, and I'm going to try to simplify as much as I can with the parentheses first. And so what this means is that m squared is to the power of negative 4, and n to the negative fourth is also to the power of negative 4. So the first thing I'm going to do is I am going to write this out as m squared to the negative fourth times n to the negative fourth to the negative fourth. And that may be a step that you might not always need to write. But once I've done that, I can remember what my property says. A power to a power means I'm going to multiply these. And so that gives me m to the negative 8th times n to the 16th divided by 2 times n, and I'm going to change the order of this, times n cubed times n to the negative 4th. That way we can see our n's next to each other. And I can go ahead and combine these right here. And I know that this has an understood exponent of 1. And I'm going to add those exponents. Whenever we're multiplying and they have the same base, we're going to add the exponents. So we have n to the 4th. And what I'm going to do next is I am going to look at my n's, and I'm going to subtract the exponents because I'm dividing two terms, n to the 16th, n to the 4th, that each have the same base. So because of that, I'm going to subtract the exponents. And so that gives me n to the 12th. And then I still have this part right here. And I'm going to do the same thing with the m's. I'm going to subtract my exponents. So I have to be careful with the negatives here. That's negative 8 minus negative 4, which is negative 8 plus 4. So that becomes negative 4. Now the key is when I'm simplifying, I don't want to leave any duplicate letters in my final answer, and I don't want to leave any negative exponents. So I'm good with the duplicate letters, but I do have an exponent. And so what we know to be true is that anytime we have a negative power, we can take the reciprocal of that, which means switch from the top to the bottom or the bottom to the top, and make that a positive power. We just have to be careful that it's only the m to the negative 4th. Anything else that's not m to the negative 4th stays where it is. And that's my final answer. Next up is adding and subtracting polynomials. And so I always recommend people to color code. So color code your like terms. When we have simple addition like we have right here, in this first example, we just want to find the like terms and make sure we carefully combine them. So I see that n to the 4th has a like term, and then I also see we have negative 1 is a like term with negative 4. And so when I do this, I'm going to start by adding n to the 4th plus negative 4n to the 4th. So that's negative 3n to the 4th. And then negative 6n squared had no like term, so we just carry it down. And then negative 1 plus negative 4 is negative 5. So it's just careful keeping track of your like terms and your negatives. Be careful here. The most common mistake I see is people forgetting that this says addition and just jumping straight to multiplying this out and foiling it. And so that's the most common thing I see. Now with this second one, I'm going to have an additional step because this subtraction sign is applying to everything in the parentheses after it. So we are subtracting 7b cubed, we are subtracting 1, and we are subtracting negative b. And so the first thing I'm going to do is carry down my first set of parentheses, and then write out what I'm subtracting. I'm subtracting 7b cubed, I'm subtracting 1, and because I'm subtracting negative b, that means I am adding b. That way I'm being really careful with my negatives. And then I'm going to go ahead and identify like terms. So I have 2b cubed and negative 7b cubed. I have negative 7b and b. And then I have 1 and negative 1. And so I'm going to combine those like terms. So 2b cubed minus 7b cubed is negative 5b cubed. Negative 7b plus b is negative 6b. And negative 1 minus 1, careful with those negatives, is negative 2. So we've now done adding and subtracting polynomials. Now we have multiplying. Notice there's no plus or minus in here, so we know we truly are multiplying this times this. And what I like to do is draw this out. Now, some of you might like to do that box method, which is totally fine. I think the fastest method is to go horizontally, but it's whatever method works for you. So I have 5x squared, and I need to make sure it multiplies by 8x, which will be 40x cubed, and also that it multiplies by negative 2, which would be negative 10x squared. And then I need to also take this negative 2x and make sure it multiplies by 8x, which is negative 16x squared. And then that negative 2x also has to multiply by negative 2, so that's plus 4x. And then last but not least, this negative 3 has to multiply with 8x, which is negative 24x. And it also has to multiply by negative 2, which is plus 6. And so once I've done that, I'm going to identify my like terms so that I can simplify here. So I see we have negative 10x squared and negative 16x squared, so those are like terms. I see we have 4x and negative 24x, so those are like terms, and those are our only sets of like terms. So I'm going to bring down the 40x cubed, combine negative 10x squared with negative 16x squared, and then again combine 4x and negative 24x, and carry down the 6. That's my final answer. Like I said, if you like the box method, you can certainly put your polynomials into a box as a way of organizing your work and making sure you don't forget anything. And so we'd get 40x cubed, we'd get negative 16x squared here, we'd get negative 24x, we'd get negative 10x squared, 4x, and 6. We get the same exact set of terms here as we do here, and then we combine like terms to get to this spot, but the box is just a tool to make sure that you don't forget any set or any pair. Last up is end behavior, and whenever you have end behavior, there's 4 ways your end behavior can go. If you have a degree that is even for a polynomial, you're either going to have both end behaviors going up, or you're going to have both end behaviors going down. If you have a degree that's odd, you are going to have it either be down and then up, or up and then down. And that's the way that you are going to tell if the end behavior is the same as each other when it's even, or opposite of each other when it's odd. And then to determine which of those two your end behavior is, you look at your leading coefficient. If your leading coefficient is positive, it's both up. And if your leading coefficient is negative, it's both down. For odd, if your leading coefficient is positive, you have, similar to a positively sloped line. If your leading coefficient is negative, you have end behavior that is like a negatively sloped line. And that's my easy way to remember it. So the key is you're going to look at a polynomial, you're going to decide, is the degree even or is it odd? And then from that, is it positive or is it negative of a leading coefficient? Once you know which of the 4 end behaviors you have, then you're going to write it in the end behavior kind of proper notation. So we're going to do a couple of examples. So we're going to start here. Here I'm looking for the highest valued exponent in our group, and that's 5. So my degree is 5, which is odd, which means I have opposite end behaviors. And then my leading coefficient here is an understood 1, which is positive. So because I have odd, I know I have opposite end behaviors, and because I have a leading coefficient that's positive, I should have something that looks like a positively sloped line. So now that I know that that is my kind of drawing, down on the left, up on the right, I'm going to go ahead and write out my end behavior statements. And I have 2 of them. One says, as x approaches negative infinity, so when x approaches negative infinity, we're talking about the left side. And so as I go to the left, I see that y is going down. So I can say f of x approaches negative infinity because it's going down. As x approaches positive infinity, that means I'm going to the right. Y is going up towards positive infinity. Sorry about that bell. And that is our end behavior statements. So let's look at this next one. We have a degree of 3 because that's the highest exponent. So our degree is odd. And we have a leading coefficient that is negative. So I should have something that looks like a negatively sloped line here. And again, it may not be a line, right? I'm just using that as a way to remember which way my opposite end behaviors go. And then I can write my statements. As x approaches negative infinity, so that's to the left, y is now going up. So that's towards positive infinity. And as x approaches positive infinity, that's to the right, y is going down. So y is going towards negative infinity. Let's look at 2 more. We have a degree. We have to be careful here because it's not in standard form. So my degree is 8, and my leading coefficient is 1. So I have an even degree and a positive leading coefficient. And so I know that that means I have, since it's even degree, I have same direction end behavior. And because it's positive, I have both up end behavior. And so I'm going to write my end behavior statements. As x approaches negative infinity, so that's to the left, what's happening? I'm going up. So I'm going towards positive infinity. And then as x approaches positive infinity, so that's to the right, I'm also going up. So that's also positive infinity. So there is my end behavior statement. One more, same thing, it's not in standard form, so we have to be careful looking at our degree and our leading coefficient. But here it is. So I have degree is even, leading coefficient is negative, because it's -7. So that means even means same end behavior, negative means both down. So because we have both down, when we say as x approaches negative infinity, we're going to the left and down, so y is going down towards negative infinity. And as x is approaching positive infinity, that's to the right, it's also going down, so y is also approaching negative infinity.